All right, I wanted to follow up on our lecture from Friday. We didn't finish. Just a quick summary. We introduced the mean value theorem, which basically said that at some point on the interior of an interval, the derivative at a point will equal the average change in that interval, that is the slope from the two endpoints. We then used that to show that we could actually classify increasing and decreasing functions on an interval using the derivative, and that is if the derivative is positive on an interval, the function is increasing, and if it's negative, it's decreasing. And then we did an example at the end of class when we ran out of time. What I want to cover here are some other consequences or other corollaries that come out of the mean value theorem. So we'll start with the following. We know that if a function is a constant, its derivative is zero. We proved that early on in the section on derivatives using the limit definition of a derivative. But this is going to go the other way. It's going to basically say that if the derivative is zero, then the function actually must be a constant. There's no other function that could have a derivative of zero. And that uses the mean value theorem as well. Okay, so we're going to start with the fact that the derivative is zero on every point in an interval, and then show that the function is a constant. And so what they do is to show, the goal here is to show that if I pick any 2 points, x1 and x2, that the value of the function at those points will be equal. Okay. And they assume that x1 is less than x2, so we're moving from left to right. We know that the function, since the derivative is zero and exists, that it's differentiable, which means it's also continuous. And therefore, we can use the mean value theorem. And what the mean value theorem says is that the derivative at some point c will equal the average rate of change between the points x1 and x2. Okay? But we know that the derivative equals zero. That was our starting point. And if the derivative equals zero, the only way for the right-hand side to equal zero is if f of x2 is equal to f of x1. That is, if the numerator is zero. Which means these functions it always has to be the same, which means it's a constant. Okay, so therefore, we can say that if the derivative is zero, the function is a constant. The second corollary has to do with the derivatives. And what that says is that if you have two functions that have the same derivative, then those functions have to differ only by a constant. They're the same function plus or minus a constant. And so what they're saying is that if f prime equals g prime at every point on an interval, then there is a constant c such that f equals g of x plus c. That is, it's just a vertical translation. Otherwise, the functions are identical. Their slopes of their tangent lines are the same at every point on the function. And the proof is fairly straightforward. And it also uses the mean value theorem. It says that let's define a new function h, which is just the difference of f and g. Whatever f and g are, it's the difference. Then by our property of derivatives, the derivative of h prime would be f prime minus g prime. We're just differentiating f minus g. But we know the derivative of h would be zero, since f prime minus g prime, well, those are always the same. That was our assumption. So that derivative is zero. But if the derivative is zero from corollary 2, this is the previous corollary, we know that if the derivative is zero, then the function must be a constant. So that means h must be a constant. But h is f minus g, but that equals a constant, and so therefore f must equal g plus a constant. Very, very simple proof, but it can be confusing as you're working through it. So I would read through that. So we have two additional corollaries. If the derivative is zero at every point in an interval, then the function is a constant in that interval. And secondly, if two functions have the same derivative, then they are the same function except for a constant. Okay, so they differ only by a constant. So now we're actually to a point where we can start to talk about integral calculus. And in particular, antiderivatives. Antiderivatives are the opposite of taking the derivative. They're actually going back from the derivative to the function which has that derivative. So I'm going to do example 7, and then I'm going to do example 8. So example 7, it says find the function f whose derivative is sine of x and whose graph passes through the point 0, 2. Well, we know if the derivative is sine of x, the original function had to be negative cosine of x plus a constant. Now this comes from corollary 3 that says, if we had two functions that had the same derivative, minus cosine of x and something else, then they would have to be the same function except for a constant. So we know that f, that is the function whose derivative is sine of x, has to be negative cosine of x plus some constant. Now what we don't know is the constant, but we do know that this function is going to pass through the point 0, 2. So we know that when x is 0, the value of the function will be 2. So we can substitute that into minus cosine x plus c and get that the constant has to be 3. So there is a unique function whose derivative is sine of x, which passes through the point 0, 2, and that unique function is negative cosine of x plus 3. Okay. Obviously, the function negative cosine of x plus 2 also has a derivative of sine of x. However, it does not pass through the point 0, 2. Okay, so we need this additional piece of information in order to get back to the original function. And we're going to find that that piece of information, that point, is called an initial condition. So it's a little bit different from taking the derivative. When we take the antiderivative, and the antiderivative here would be negative cosine of x, we do not get a unique answer. We get, in this case, an answer plus a constant. And the constant could take on any value. And it would still be a function that has a derivative of sine of x. In order to get a unique answer, we have to add another piece of information. And in this case, it is the initial condition, the point 0, 2. Okay. So in that example, the function, and we're going to see this notation, this function big F of x is what we call the antiderivative. So in the previous example here, the big F of x was negative cosine of x. And so it is the function that when you take its derivative gives you little f of x, which in our case was negative cosine of x plus c. Okay. This process is anti-differentiation. Okay. Now one of the issues and one of the things you have to recognize is that if we have little f of x, then big F of x has infinitely many derivatives. That is, whatever big F is, we can add any constant to it, and it will produce the same F. Okay, so there is not a unique antiderivative. There is a whole family of antiderivatives that differ by a constant. Okay. And that's going to take us to this last example. I'm actually going to skip to another page here. But it has to do with finding velocity and position, that is, functions for velocity and position given acceleration. Okay, so I'm going to go to that example now. So the first of the two problems said we're going to assume the acceleration is 9.8 meters per second squared, which is just the acceleration due to gravity. And in this particular one, they told us that the initial velocity, that is the velocity at time 0, was 0, because they said the object was at rest. And they told us the initial displacement or position at 0 was also 0, because they said the initial height was 0 meters. And they want us to find functions for velocity and position. Okay, so we can now work backwards. If the acceleration is a constant, 9.8 meters per second squared, then the velocity function had to be 9.8 t plus a constant. This is the antiderivative, and this is the constant. So any constant value here, if I took the derivative, would result in an acceleration of 9.8. But they also told me that the velocity at 0 was 0. So if I plug in 0 for t, I find that in this case c has to be 0. So the unique velocity function for an object falling from rest due to the force of gravity is 9.8 t. Now I can repeat that same process and find the antiderivative of 9.8 t. Well, that would be 4.9 t squared plus a constant. Right? If I take the derivative of s of t here, I get 9.8 t. Now to find out the value of the constant, I have to plug in the value at 0 again, which is 0, and I find the constant has to be 0. So in this case, when I'm initially at rest and at an initial height of 0, this would be the velocity function, and this would be the position or displacement s of t. Okay. Now let's do a slightly more complicated problem. Same idea, but we now have an initial velocity of 1 meter per second. So we're not at rest, we're actually moving at a speed of 1 meter per second. So as before, the velocity function is 9.8 t plus c, but now at 0, when t is 0, the velocity is actually 1. So if I substitute there, I see that c has to be 1, and my velocity is 9.8 t plus 1. So now I have a different unique velocity function based on the initial velocity of the object. I can repeat the process for my position, and I can find that my position function is 4.9 t squared plus t. Right? That is the antiderivative of the velocity that has a constant such that the initial position is 0. We can actually generalize this to get back to a function that you should have seen before, and that is the general equation for the position of an object falling at an initial velocity v0, that could be any value, and at an initial position s0. And so we can repeat this process. If the acceleration is 9.8, then the velocity function would have to be 9.8 t plus some constant. At t equals 0, that constant has to be v0. So the general velocity function is 9.8 t plus v0. If v0 is 0, then it's 9.8 t. We saw that in example A. If v0 is 1, then it's 1. We saw that in example B. Now if I take the antiderivative or find the antiderivative of v, I get an expression for c, but at t equals 0, c has to be s0, and this gives us the final general formula for position of an object with an initial velocity of v0 and an initial displacement of s0. So with this material, you now have everything you need in order to move forward on the assignment, and when you come to class on Monday, our focus is going to be on any questions or resolving any issues related to this material. I'm not going to redo these examples in class on Monday.